Hello everyone. So this is the last video of the series on tensor analysis. What I'll do now is to show an outline at least how the various expressions for the gradient and divergence etc. of vector and tensor fields are defined in curvilinear coordinates. In the previous video we saw how the notion of a coordinate transformation naturally gives rise to the notion of a coordinate curve, which in turn gives rise to the coordinate tangent vectors, which forms the basis at every tangent space of R3. Okay, let's build upon that right now. So let's consider a scalar field to start with. F from R3 to R. So what this means is that f takes three real numbers x1, x2, x3 and returns one single real number f of x1, x2 and x3. So f acts on this, and remember this is a Cartesian description and returns a real number of this particular form. And now what we want to do is we want to study the same problem in the setting of a curvilinear coordinate system. So let's consider a coordinate system u comma psi. So remember that this means that u is an open subset of R3 and psi is a smooth and invertible map from u to an open subset of R3 such that the inverse is also smooth. Okay? Such a psi is called as a coordinate system. Now, if f is a function from R3 to R, so certainly f is also a function from U to R. Okay, so it's just a restriction of f on U. And what we can do is, instead of expressing f in terms of x1, x2, x3, we can alternatively express it in terms of the transformed or the new coordinate system x1 bar, x2 bar, and x3 bar. So how do we express this? How do we express f in terms of these new coordinate systems? Coordinates, okay. So one way to think about it is to look at this thing. U is a subset of R3 and f is a function which acts on this and returns a real number. Okay, so this I'm going to draw a commutative diagram to illustrate this idea. And psi is a coordinate system. So what in particular, psi transforms U to an open subset psi of U of R3. So this immediately tells you that this map, which goes from psi of U to R, is nothing but f after psi inverse. Okay, and if you follow the commutative diagram, it tells you that f of x1, x2 and x3, okay, which is basically this leg of the commutative diagram, equals f after psi inverse of x1 bar, x2 bar and x3 bar. Okay, so one way to think about it is that you can just think about it x1, x2, x3 as psi inverse of x1 bar, x2 bar, x3 bar. So this is nothing but f of psi inverse of x1 bar, x2 bar, x3 bar, which is exactly the same as what is written here. Okay, that's a simple way to see it alternatively. Good. Now in the interest of notational simplicity, I'll notate this function f after f psi inverse as f bar. Okay, again, the bar quantities of the bar refer to symbols with respect to the new coordinate system. So what we see is that f as a function of x1, x2, x3, which is the Cartesian description, can alternatively be written in the new coordinate system as f bar of x1 bar, x2 bar and x3 bar. It's important to note that f and f bar could be very different functions. Okay, the representation of a function should not be confused with the function itself. Okay, the representation of a function depends on the coordinate system. Okay, now how do we go about defining the various derivatives of like say the covariant derivative, the gradient, divergence, etc. How do you define that? in this context, in the context of curvilinear coordinates. And the starting point is exactly the same. The recipe is exactly the same. Recall from the earlier discussion that we start always with the generalization of the directional derivative called the covariant derivative. Okay, so we start always with the covariant derivative, and we deduce the gradient from that, the divergence from that, and the curl from that, and so on. Okay, that's the standard procedure. But in the context of the scalar function f, let's compute the covariant derivative of f at the point x bar. So let me say the covariant derivative of f bar at the point x bar along a direction h. Okay, and just to make it clear that the gradient operation, the nabla operation here is with respect to x bar. I'm going to use a nabla bar, okay, a del bar of in this process. So what does this quantity mean? It's nothing but this. It's defined as follows. It's the derivative with respect to s of f bar at x bar plus sh as s goes to 0. Okay, it's a very simple definition. It's exactly analogous to what we did in the earlier case, except that now we are looking at a different function f bar which depends on x bar. That's it. Okay, good. Now again, the chain rule is obvious, so we can write it as summation of partial f bar of x bar with respect to x bar j, let's say, times hj. Now here comes the interesting part. Remember that in the Cartesian coordinate setting, we define the gradient as follows. If this quantity is the gradient, or is can be written as something dot h, then that something is basically the gradient. Okay. And so how do we go about doing this in the context of Cartesian coordinates? That was very easy. You could just write this as the in a very simple form. For instance, partial jf ej dot hiei. That's it, and you're done. But in curvilinear coordinates, since the bases g1, g2, and g3 are not orthogonal in general, remember that once I have this a given coordinate system, I can construct the coordinate basis g1 of x bar, g2 of x bar, and g3 of x bar. And this is nothing, it's a basis. Remember, it's the basis of tx bar of R3, or rather yeah, tx bar of R3 is reasonable in description. Okay, good. So but the problem is that in general this basis g1, g2, g3 is not orthogonal. So you cannot write this directly as the inner product of partial f over partial j and hj, and you have to be a little more inventive in this case. Okay, so so let's write it down properly. So the first thing is I'm going to write it as g. I'll first write down the expression and then I'll explain how it works. Partial f over partial x bar I, and then gk, the whole dotted with summation, say some h j gj. And how do we justify this? How do we go about justifying this? So notice that if I take the dot product of these two terms, you're going to have the dot product of these two vectors. So it's going to be this is going to be summation of gik partial f bar by partial x bar I. Again, when I write partial f bar by partial x bar I implicitly assume that this is a function of x bar. Okay, so it's assumed here. Okay, okay, so it's going to be times hj, this is the quantity over here, times gk dot gj. Okay, so it's gk dot gj, which is nothing but gkj. Okay, so it's going to be gkj. But g superscript ik times g subscript kj is nothing but delta ij. Okay, so this is nothing but delta ij. So you immediately get this expression. So this is going to be partial f bar at x bar by partial f x bar I. So is it? Okay. partial x bar I times delta ij hj. Okay, and this is nothing but this expression over here, which is summation of partial f bar x bar by partial x bar j hj, which is exactly the expression that you have here. And so that justifies why you can write it in this particular form. But notice how it's not a trivial as in the case of Cartesian coordinates, but you have this extra term over here on the right. So you have to be careful about how you write it. But once you write it in this particular form, notice that this quantity over here is nothing but h. So you have managed to write the covariant derivative as the inner product of some quantity dot h, and so the quantity here should be the gradient. Okay, so that immediately tells you that the gradient of f bar at the point x bar, and again to note the to represent the fact that gradient here is with respect to x bar, I'm just going to use this strange symbol gradient over bar. Okay, this is just to distinguish this gradient from the gradient with respect to the Cartesian coordinates. Not the best of symbols, but it works for our purposes for now. Okay? So this tells you that the gradient has the following expression. It's going to be summation g I k partial f bar x bar by partial x bar I g k. Okay, remember gk is a vector, whereas g superscript ik is a number. Okay, so that's the expression for the gradient in the context of general curvilinear coordinates. The description so far has been quite general in terms of I have not given you any concrete illustration of how a coordinate system would look like. So let's look at a simple example before we proceed further, because that would help you to make the ideas very concrete. Okay, so let's consider an example. And here I'm going to consider what is called as a cylindrical polar coordinates. Okay, coordinates, and this works roughly as follows. You want to basically define, remember a coordinate system is defined as a pair u comma psi, where u is an open subset of R3 and psi is basically a function. Okay, so I'm going to define the function as follows. I define x1 bar as square root of x1 square plus x2 square. Let me first write the function psi and then tell you the domain of definition. Okay, so this is just it's going to be tan inverse of x2 by x1, and x bar 3 remains as it is. Okay, this is your standard cylindrical polar coordinates. You might have seen x bar as r, and tan inverse of x2 by x1 is nothing but a theta, and x3 bar is nothing but a z. Okay, so this is the standard notation, so but I have it here. And of course the fact that this equation involves the tan inverse of x2 divided by x1 tells you that x1 cannot be 0. Okay, so and that tells you that the domain of definition of this particular coordinate transformation is some subset of R3. For instance, one way to think about u is R3 minus the set of all x1, x2, x3 such that x1 equal to 0. So it's an entire plane in R3. So if you define R u in this particular fashion, and psi, this prescribes psi from u to r, u to R3, then this is an example of a coordinate transformation. And so let's compute the expression. Suppose I give you a function f which depends on 3 variables, x1, x2 and x3. Okay, so in other words, f is a function of this particular form. F is a scalar field which goes from R3 to r, and we know that the expression for the gradient of f in Cartesian coordinates in Cartesian coordinates, the gradient of f at the point x is nothing but summation partial f at x with respect to partial xi ei. So what happens in cylindrical polar coordinates? what's the corresponding expression for in this particular case. Okay, and we are going to use this expression over here to compute the gradient. And notice that that involves in particular finding out what f bar is, and then finding out what gik is. Now f bar is nothing but a simple transformation of coordinates, but the more important quantity is g bar. So how do you go about computing g bar? Okay, and remember that from our previous lecture that you had an explicit expression for gi. Okay, so gi, let me recollect it here. Gi was nothing but summation of partial x, say j, of x bar by partial x bar I e j. Okay. So if you can express the x in terms of the x bar, then the ith partial derivative of that is going to give you the vector gi. So how do you compute this here? So for that you first need to invert this relationship. Okay, let's do this. It's actually quite straightforward. All you have to remember is that if this were the case, then you can see that x1 is nothing but okay, let me write it in terms of a more familiar setting. It's going to be r cos theta. X2 is going to be r sin theta, and x3 is going to be z. Okay, so you can also write it in terms of x1 bar and x2 bar. It's going to be x1 bar, the cosine of x2 bar. This is going to be x1 bar times the sine of x2 bar, and this is just going to remain as x3 bar. Okay, so now we have expressed x1 in terms of x1 bar, x in terms of x bar, and vice versa. Again, notice that this is valid only on psi of u, not the whole of R3. Okay, it's a local coordinate system. And once you have this, you can go ahead and compute the basis vectors gi. For instance, g1 is nothing but summation partial xj of x bar with respect to partial x bar 1 ej. And so that immediately it's a very simple calculation. It tells you that this value is the cosine of theta times e1 plus the sine of theta times e2. Okay. Now again, you can compute g2 in an entirely analogous manner as minus r times sine theta e1 plus r times cos theta e2. Because all you have to do is you have to take the derivative of the coordinate functions with respect to r2, which in this case is x bar 2, which in this case is just theta. Okay, and similarly g3, in this case that's very, very simple. It's just going to remain exactly the same as e3. And now comes an important point. Notice that in this case with g1, g2 and g3 defined like this, you can easily verify that gi dot gj equal to 0 whenever I is not equal to j. So it turns out that in this special case, the tangent of the coordinate curves are indeed orthogonal. That's not true in the general case. Okay, in the general case they may not be orthogonal, but in this case they are orthogonal. In fact, this is true even for the other popular coordinate system, which is this set of spherical coordinates. I'm just giving the derivation in cylindrical polar coordinates because it's much easier mathematically. The calculation is a little more involved in the context of spherical coordinates. Okay, so now once we have this, so let's compute the matrix G. Remember, G is the matrix whose entries are Gij. Okay, which is nothing but Gi dot Gj. And right off the bat, you know that the diagonal elements are the only non-zero elements. The off-diagonal elements are precisely these elements, Gi dot Gj, when I is not equal to j, and they are 0. Okay, and so what you're left with is the first diagonal is G11, which is basically G1 dot G1, that is just 1. Okay, so this is 0 and this is 0. Again, the off-diagonal elements are all 0. What is G2 dot G2? So you see that there is an r squared term, but the rest of it is just a unit vector, so it's going to be r squared. And G3 dot G3 is again 1, trivially. Okay, and this also implies immediately, because it's a diagonal matrix, you can take the inverse of G, and that's nothing but 1 0 0 0 1 over r squared 0 0 0 1. that's the inverse of G. Again, notice that you have to define the domain of the inverse transformation and the forward transformation appropriately. Otherwise, 1 over r square would be 0. So you have to make sure that that possibility does not arise. Okay. Now, once you have this, then the expression for the gradient is quite straightforward to calculate. So notice that the elements here are G subscript ij, and the elements here are G superscript ij. G superscript ij is nothing but G inverse of ij. So it's just a special notation in this case. And now that we have all these things, then we can go ahead and compute the gradient of f bar at x bar. Okay, so the gradient of f bar at x bar is nothing but the gradient of f bar of r, theta and z. Okay, that's just the x bar coordinates. Okay, so how do you go about doing computing this? And so you just have to just apply this formula that we derived earlier. So no, it's nothing but the product of the matrix components of the inverse of G and the gradient of f bar. Okay, so it's very straightforward to compute, and you end up with the following expression. So it's going to be partial f bar by partial r. Again, I'm omitting all the arguments, but when I write f bar, I implicitly mean f bar is a function of r, theta and z. Okay, so you have g1 here plus 1 over r squared partial f bar over partial theta g2 plus partial f bar by partial z ez g3. Okay, so g3. Okay, good. Okay, so now that we have this expression, notice that g1, g2 and g3, they are orthogonal, but they do not form an orthonormal basis. Okay, because the norm of g2 is actually r squared. It's not 1. So the easiest way to make it as r squared, the norm 1 is to redefine a set of new basis vectors. It's basically a Gram-Schmidt orthogonalization. But since these are already orthogonal, the process becomes very simple. You just have to divide each of gi divided by their norms. Okay? So in particular, I'm going to define er as g1 divided by norm g1, which is exactly the same as g1, e theta as g2 divided by norm g2, which is nothing but g2 over r, and ez as g3 over norm g3, and this is nothing but g3 itself, because norm of g3 is 1. Okay, so with this definition, you see that the gradient of f bar at the point x bar is simply the derivative with respect to r times er plus 1 over r times the derivative of f bar with respect to theta, e theta, plus the derivative of f bar with respect to z, ez. So that's the familiar expression that you might know from your from various earlier encounters with the gradient. So now you see that you started off with a gentle curvilinear coordinate system, and this is an example of how you would actually compute it in a very specific example, the specific example of a cylindrical polar coordinate system. Okay. Now let's move on to the next type of tensor field, which is a vector field. So what we want to do is, we are given a vector field v from R3 to R3. Again, notice that it's technically the tangent bundle of R3, but I'm simplifying it and using the flat structure of R3 to just write it in this particular fashion. And earlier we saw that v of x could be written in the Cartesian setting as vi of x ei. But with respect to an arbitrary coordinate system u comma psi on R3, we can write this as v bar I at the point x bar times gi at x bar. So notice that it's the important point to notice here actually is that both the component of v and the basis vector of v are dependent on x bar. Okay, so as you move from one point to the other, from say x bar to a neighboring point, both the components of the vector field and the basis vector change. So you have to be extra careful when you take the covariant derivative. Again, recall that when we want to compute the various tensorial quantity, various derivative quantities like the gradient, divergence, curl, etc., the starting point is always the covariant derivative. So let's compute the covariant derivative of v. So I'm going to write as v bar of x bar. Okay, so this is v bar of x bar. Okay, I write it like this in the direction h. Okay, so this is nothing but the directional derivative at s equal to 0. Okay, of this the expression for v bar, which is nothing but the summation of vi bar at x bar. Okay, it's actually x bar plus sh, x bar plus s times h, and here is the important point, it's gi of x bar plus sh. Notice that unlike the Cartesian setting where both where ei is constant, in this case both the component vi and the basis vector gi have a dependence on x bar, and hence you will have an x bar plus sh term in this case. Now once you understand that, the rest is straightforward, because all you have to do is apply the chain rule, and again you have two terms over here, so you apply the product rule and then apply the chain rule in each case. So the first term here would be the derivative of the first quantity vi bar, so it's going to be summation of partial vi bar at x bar divided by partial say x bar j, and you're going to have hj, and the other term just becomes gi of x bar when evaluated at s equal to 0, plus the second term is again it's going to be vi at x bar, because when you said s equal to 0, it's the same, and the partial derivative of gi at x bar with respect to x bar j, and then the derivative of the argument with respect to s, which is nothing but hj. Okay, but you know what this quantity is? This quantity over here is precisely what we defined earlier as a Christoffel symbol. Okay, so we can write this as the partial v bar I x bar over partial x bar j hj gi of x bar plus summation vi of x bar, and this can be written in terms of Christoffel symbols as vi of x bar gamma k I j gk hj, and now notice that this has hj and gi, whereas this has hj and hj and gk. Okay, so how do you flip this around? Okay, so all you have to do is you have to replace this the index k with the index I. Okay, and just relabel the indices. So I'll just write the final expression. So this is going to be summation of partial vi bar at x bar by partial x bar j. Okay, and I'm going to take hj gi of x bar totally outside, so I need something here, and outside this expression I'm going to have hj gi of x bar. Okay, so you already have an hj here, so the j index remains as it is in this expression. The j index remains as it is, but instead of gk you need gi. Okay, so I'll replace k with I rather, so it's going to be gamma k, and of course then I have to replace I'll replace that with say k, so it's going to be kj and vk at x bar. And again remember, this is also evaluated at x bar. The Christoffel symbol is also dependent on x bar. Okay, so And now once you have this expression, if you can write this as the inner product of something dot h, then that something is the gradient. Okay, so how do you go about doing this? And the technique here is exactly the same as what we studied earlier. Okay, so in the sense that you have to replace there will be an extra term of this particular form. Let's say you have this, you see this term over here, there's a g superscript ik over here, exactly a term of that form will appear over here. Okay, so that's it's just let's just write it down. So this is going to be the inner product of something dot the h j, so let me write as h j g j. Okay, so I need to have some quantity over here. Okay, so but I already have a gi. Okay, the remaining quantity has to be some g over here. So how do you go about writing this? Okay, so let me write the final expression. So it's going to be sum of g, so I'll write this as a, and I ideally want a j over there, gaj, okay, or a gja, and g is symmetric, so it doesn't matter how you write it, times the rest remains as it is, partial v bar I at x bar by partial x bar j plus okay, I need some more space, so it's going to be plus gamma I k j vk of x bar times gi tensor product ga. Okay, and it's a straightforward exercise to verify this, because when you multiply these two, ga and gj pair with each other, so it's going to be gi times ga dot gj, that's delta aj. Okay, and so delta aj, and if I have this particular quantity over here, that will cancel out with each other. Okay, so and you get the final expression for the gradient from this simple calculation. It's a very straightforward computation. Good. Okay, I mean this is probably not the best index. I mean I should use a different index here to avoid confusion, so maybe you can write it as say hk gk. Okay, I already used k, so maybe some sorry about this, you just need a different index, so maybe hb gb. Okay, why not? So once you have this, so you know that ga dot gb is the, gab, so when you take the dot product, you have gi times this quantity gab, that's going to give a term like gab times gi, but when you pair gaj with gab, you get a delta jb, so you replace the b here with the j, and you recover back this expression. Okay, so it's a straightforward exercise in index manipulation, and so I'll leave that to you to verify in full detail. Okay, good. So once you have this, then it's straightforward to read off the expression for the gradient. So you can see that the gradient of v at the point x bar. Okay, so I'll just write it like this so that it becomes clear what the meaning is going to be summation of g a j times partial v bar I at x bar over partial x bar j plus gamma I k j vk of x bar. Okay, oh sorry, it should also all be v bars. I've been missing out on the v bars over here. Okay, good. I think yeah, even here it's going to be v bar, just a typo. Okay, so now you have this expression, and of course that's not the full thing. You also have gi tensor product ga. So notice that the gradient is a second order tensor, exactly as you would have expected. And notice also how this expression is distinctly different from the corresponding expression for Cartesian coordinate systems. Okay, for Cartesian coordinates, you did not have this term at all. The second term was not existent at all. And that's simply because all the Christoffel symbols vanish uniformly in the context of a Cartesian coordinate system. It's a very, very straightforward exercise to verify that, so please do that. And again, notice how the expression for the covariant derivative is significantly more involved than that for the case of a Cartesian coordinate system. Okay. Okay. And now once we have this, we can, for instance, compute all the other quantities like divergence and curl based on the same recipe. For instance, to compute the divergence of V bar, so again I'll use divergence with the over bar to say that it's a divergence with respect to the new coordinate system. So if I look at this particular quantity, all I have to do is I have to contract I and A over here. So wherever I see an A, I replace it with I, and that's it. Okay, so it's going to be summation of G ij, okay, times partial V bar I by partial X bar j plus gamma I k j V bar k. That's it. Okay, so now this is the expression for the divergence of the vector field in curvilinear coordinates. Notice again that this expression is distinctly different from the expression that you had in Cartesian coordinates, which was just summation partial vi by partial xi. But now you have all these additional terms and an extra prefactor, which is g superscript ij. And this is why I know you might have seen expressions for the gradient and divergence in cylindrical coordinates or spherical coordinates, and you will see that they often have a very non-trivial form, and that is mainly because of the fact that the basis vectors of the tangent space at each point varies as a function of x bar. That's essentially the idea. Okay, everything follows from that. And again, in the interest of time, not in time, but rather in the interest of clarity, I will give you an example. So let's take the same example that we considered earlier. So suppose I consider cylindrical polar coordinates now. How do I represent the components of a given vector field? How do I represent the gradient or divergence of a given vector field? Okay, the full calculations are quite cumbersome, so what I'll do is I'll just outline the key ideas, and then I'll leave it to you to work out all the details. Okay, because it's really a straightforward exercise, and but there is one important thing that needs to be understood here. Okay, suppose I write V bar of x bar, okay, with respect to the coordinate basis as follows. So it's going to be summation Vi bar of x bar times Gi of x bar. Okay, remember we computed G1, G2 and G3 earlier for cylindrical polar coordinates. Okay, so G1 was simply cos theta E1 plus sin theta E2. G2 was minus r sin theta E1 plus r cos theta E2, and G3 was just E3. Notice that these are not orthonormal, but they are only orthogonal. And to make it orthogonal, we introduced an orthonormal basis. To make it orthonormal, we introduced this new basis ER, E theta, and EZ. Okay, good. It's exact. ER is the same as G1. E theta is G2 divided by R, and EZ is the same as E3. Okay, so a given vector can be written either as V bar 1 G1 plus V bar 2, and I'm going to put a dash here. I mean, it's just a differentiation symbol. It's not the differentiation symbol. It's just a symbol to distinguish V bar 2 from V bar 2 dash. That's it. It's just a symbol. There's no meaning to it. Okay, plus V bar 3 G3, or I can write it as well as V bar 1 ER plus V bar 2 E theta plus, okay, write the plus properly, plus V bar 3 EZ. Now if I write it like this, then it's immediately obvious. Okay, let me put a dash over here just to give So the components with respect to G1, G2, G3 are V1 bar dashed, V2 bar dashed, and V3 bar dashed. And the components with respect to ER, E theta, and EZ are V1 bar, V2 bar, and V3 bar. Okay, so it follows from a straightforward comparison that say V1 bar equals V1 bar dashed. Okay, now E theta G2 is nothing but E theta divided by R. Okay, so immediately tells you that V2 bar is the same as V2 bar dash divided by R, and V3 bar is the same as V3 bar dashed. This follows by direct comparison. And typically when people use curvilinear coordinates, especially orthogonal curvilinear coordinates, they always adopt this representation. Okay, whereas when we directly apply the setting of a coordinate curve and then the coordinate tangents, we end up with this representation, the first representation. Okay, this representation. So you need to be careful about which representation you choose, and it's always important to convert your final result to the standard representation, which is in terms of ER, E theta, and EZ. Okay, good. Now, once this idea is clear, the rest is a routine application. Okay, so all you have to do is you have to apply this formula to compute the divergence. You have all the ingredients that you need except for the Christoffel symbols. How would you compute the Christoffel symbols? For cylindrical polar coordinates, so for Christoffel symbols are nothing but gamma k ij, and this is nothing but summation of x, say L of x bar divided by partial x bar I partial x bar j times partial x bar k of x divided by partial xl. This, but this turns out to be a very non-trivial computation, because you need to sum an L for each choice of I, k, I, and j. I need to compute these quantities, and it's a very tedious calculation. But luckily, in the context of orthogonal curvilinear coordinates, there is a shortcut here, okay, which is that you can directly differentiate these expressions for G1, G2, and G3, and use the defining property for the Christoffel symbols to compute them. So remember that the entire purpose of introducing the Christoffel symbols was to compute the derivatives of the tangent vectors, and these were defined so that you have the following equation: Ij, Gk. That's the definition of the Christoffel symbols. But luckily for us, the expressions for G1, G2, and G3 are known. So you can easily compute the Christoffel symbols as follows. So this tells you in particular that if, for instance, partial G1 divided by partial R, this is x bar 1. So I should have translated. Okay, good. So so partial G1 divided by partial R, for instance, is 0. Partial G1 divided by partial theta, partial G1 over partial theta. I should not say divided by partial theta. It's not division. Okay, so it's partial G1 over partial theta is going to be minus sine theta E1 plus cos theta E2, but this is nothing but G2 divided by R, or it's nothing but E theta. It's a very straightforward computation. And similarly, you can compute the partial derivative of G1 with respect to Z, and that's going to be 0. Okay. And likewise, you can compute the derivatives of partial G2, derivatives of G2, and the derivatives of G3, and that will give you all the Christoffel symbols. Okay. And how do you get the various Christoffel symbols? Remember that, for instance, this equation tells you that the final equation for G bar the partial of Gi with respect to x bar j should be some linear combination of gk's, and the coefficients are basically the Christoffel symbols. So this tells you that all the coefficients are 0 here, for instance. This again tells you they are 0, but here one of the components is non-zero. Okay, so this way you can actually compute all the Christoffel symbols explicitly in this case without worrying about the full expression over here. And what do you get at the end of it? Again, I'll summarize the final result. So you're going to have gamma 2 of 1, 2 as 1 over r. Okay, and this is the same as gamma 2 of 2 1. Remember, it's symmetric with respect to I and j. And then you have one more quantity which is gamma 1 2 2, okay, which is minus r, and all the rest are 0. Okay, let me include a blank page. Okay, we are almost done. So once you have this expression for gammas, all you have to do is substitute the corresponding expression in this equation for the divergence, or this equation for the gradient, to compute the appropriate expressions for gradient and divergence in both in the cylindrical polar coordinates. Okay, again, that's a good exercise for you, so I'm going to leave it open as an exercise. But what I'll do is I'll write the expression for the divergence alone, okay, because that's a very useful expression that we will encounter later on. So the divergence of v bar at x bar, again I'm using the bar over the divergence to represent the fact that this is the divergence in cylindrical polar coordinates, has this very neat form at the very end. Okay, it's going to be 1 over r partial over partial r, r v bar 1 plus 1 over r partial v bar 2 over partial theta plus partial v bar 3 divided by partial z. Okay, and again, it's very important to note that these components that you see, v1 bar, v2 bar and v3 bar, are with respect to er, e theta and ez, not g1, g2, g3. Okay, that's important to keep in mind. Again, once you have the divergence, you can compute the curl from that using the standard procedure, but the expression for curl is even more cumbersome. But you will see that conceptually there is no difficulty at all, because all that you need to know is just the covariant derivative and how the various other terms are defined with respect to that. Okay, and once you have the covariant derivative, you have these general expressions which are given here. Okay, that's enough. So if you are given a particular coordinate system, you can always go ahead and work out all the details. Okay? And if you're doing it for the very first time, I encourage you to work out these things in full detail. Okay, that way you will get a very good practice with deriving in both working with indices, calculating Christoffel symbols, and so on. So it'll be a good practice. Now, before I end, I'll very briefly talk about how you do the same thing for tensor fields. Okay. Again, the equations here become extremely unwieldy. So again, in the interest of time and simplicity, I'll consider a simple case. Suppose I consider a second order tensor. Okay, so t is a second order tensor, which means that it takes an element of R3 and gives you an element of T2 of R3. So this essentially means that it's a second order tensor field. So at each point I have a second order tensor which eats two tangent vectors and gives me back a real number. Okay, so in terms of the Cartesian representation, this would have an expression as so let me write it like this. So it's going to be t of x is going to be summation of t bar ij of x ei tensor product ej, whereas with respect to a general coordinate system, there's no bar over here. Sorry about that. So it's going to be t ij. And finally, if you write it in terms of a generalized coordinate system, it's going to be t bar ij of x bar gi tensor product gj. Okay, so how do you take the covariant derivative? So clearly, if you know how to take the covariant derivative, then you're done. Right. So again, it's very straightforward. So if I look at the covariant derivative of t, okay, it's t bar. It's along the direction h. This is nothing but d over ds at s equal to 0, okay, of this quantity summation of t bar ij of x bar plus sh, and this is where the distinction comes. So you have gi, which is also a function of x bar. Okay, so it's going to be g bar plus sh. Tensor product gj is also a function of x bar plus sh. Simple enough. And now you apply the chain rule. So you first take the derivative with respect to this, and then you take the derivative with respect to this, and finally with respect to gj. Okay, so it's a very simple expression. So it's going to be the summation of partial t bar ij of x bar divided by, say, partial x bar k times hk, and the rest remains as it is, gi tensor product gj plus, now I take the derivative with respect to gi, so it's going to be ti remains as it is, so it's going to be t bar ij of x bar, and then it's going to be partial gi divided by partial x bar j, but that you can write in terms of the Christoffel symbols. Okay, so it's going to be partial gamma k I j, and then it's going to be gk and hj. Okay, tensor product gj. Okay, let me also mention that this is at h. Okay, gk of x bar hj times gj of x bar. Okay, notice that this is h bar is a constant, so it actually comes out of this expression. So it's going to be gk of at x bar, tensor product gj of x bar, and then there is a final term which is nothing but you take the derivative of the last term, which is gj. Okay, so it's going to be tij of x bar, gi of x bar, tensor product, and you just take the derivative of this with respect to, let's say, k. So it's going to be gamma l jk, then you have gl and again at x bar, then times h, taken hk. Okay, that's it. Okay. Now what you can do is you can change the indices and write it as, one giant quantity dot h. If you can write it like this, then this is the gradient. The quantity inside is a gradient. Again, I'm going to leave it as an exercise for you to complete it, because it's a very, very useful exercise in index manipulation, and that will serve you a long way. And at least once in your life you should do it. I mean, if you're doing it at least for the first time, do it. Okay. And once you have the gradient, you can compute the divergence, and from that the curl. So if you want to get some concrete practice with these kind of problems, I encourage you to work out these expressions in say cylindrical polar coordinates. Okay, I'm going to skip giving out all the expressions, because the expressions are just very long, and just by looking at the expression you're not going to learn anything meaningful. But what is really important is to learn the process by which you are able to obtain these various relations, and that is quite straightforward here. Always go back to the basics. You start with the covariant derivative, and for the covariant derivative you just have to take the variation with respect to a small displacement about the base part, and that's all there is to it. And so with this I'll end this short lecture video series on tensor analysis. And what we have covered in this set of videos is basically the what a vector, a scalar, a vector, and a tensor field mean in three-dimensional Euclidean space, and how you would represent them. The simplest way to represent them is in terms of the inbuilt Cartesian coordinate system, but depending on the application you can also use a variety of different curvilinear coordinate systems. The most common ones are the cylindrical polar coordinates and the spherical coordinates. I have given some illustrations of the cylindrical polar coordinates here, but the spherical coordinates can also be done in exactly the same manner. And in all these cases we follow a standard recipe, which is that we first compute the covariant derivative, and from the covariant derivative we deduce what the gradient is. Once you have the gradient, you can compute the divergence by a contraction operation, and once you have the divergence you can compute the curl by means of a recursive definition. That's it. So all the key quantities that you will encounter in many applications can be computed like this. And again, I have left out the precise expression of a variety of terms here and also skipped the details of some calculations here, and that is intentional, okay? Because unless you put your pen to paper and work it out, you will not truly understand it. So please work it out. And with this, I'll stop this set of video lectures on tensor analysis.